Okay, well, great to be back in ITAMP. I haven't been here for a few years. This is a real gem for the field to have this facility, this program. I've decided to talk today about some of our recent work on polar molecules. It will be most of my talk. I had been a little too ambitious. I probably won't be able to cover the heteronuclear atomic trimers or neutrons. No, I probably have a little time for the neutrons. I saw nuclear physics mentioned, so I have to do something in our nuclear physics interests. So let's, again, thanks to NSF for supporting this or in the past. This is my group a couple of years ago, and some of the key characters today. Ahmed Yalkamshishi was involved with the dipole project. Shaimal Singh was and still is pushing it forward. And on the neutrons, this is Michael Higgins carrying the ball, who's now a postdoc with Jose Dincao. And we have a good time in my Spider-Man room in our home in West Lafayette. What got us interested was the experimental program of Sebastian Will at Columbia, who approached us because they were seeing 3 body losses as they were trying to make a Bose-Einstein condensate of their polar molecules. And this was really limiting what they could do. And this led to this paper, which was published on Christmas Eve last year. And it's continuing with Shaimal Singh. And if any of you are looking for a good theory postdoc, he might be someone to approach. He'll probably graduate next May. Yeah, this is the abstract of the paper that came out. So, of course, it's been kind of a holy grail for a long time to make a quantum degenerate gas of molecules in their ground state. There was success with the KRB fermionic degenerate gas in Jun Yi's lab now 6 years ago, and but not a BEC until this recent work of Sebastian Will. So some of the reasons why this is difficult is that you have a huge phase space when you collide 2 polar molecules together, and this really sort of leads to sticky collisions and reactive losses that take off. All sorts of complicated physics goes on, and it's been studied a lot, especially by John Bone, all the difficulties with this. And so you have the kind of very, very far away, you have a non-interacting region, but the long-range dipolar interactions, which go typically much farther than the van der Waals in atom-atom interactions. And then you have this very complicated reactive region that really none of us hope to describe, at least currently, beyond maybe statistical methods for that very short region. So in order to have any hope of making a Bose condensate of polar molecules, you have to get rid of the monster somehow. And well, one way is to bring in a shield of some sort to do that. And there have been some theoretical proposals for how to do this over the years. Many theorists and experimentalists have worked on this. In particular, there were proposals for a static field shielding and for microwave shielding. The Columbia group was implementing a microwave shielding technique. And these are some of the sample of the kinds of papers where people were inventing these types of shielding methods that turned out to actually work really beautifully. This is the basic idea. You want to have a microwave that's going to dress the individual polar molecule Hamiltonian by mixing in this excited rotational state with some detuning and some Rabi frequency. You can go to the eigenstates of this, and you can even prepare the molecules in like this plus state, which has an advantage that it will lead to repulsive interactions, as I'll show you in a minute. It gets a little more complicated when you have ellipticity, and the Columbia group did have a little ellipticity, had to be taken into account. But the bottom line is, at the end, you have this one potential curve, which due to an avoided crossing with this Greene curve, this leads to this. Basically, the molecules will adiabatically tend almost all the time to follow this repulsive wall potential. I don't remember why I wanted to have this blank slide. That's a problem in borrowing slides from a graduate student. He's put all this in a very fancy way. So anyway, this is our Hamiltonian that we're going to tackle if we use the quantum mechanics. And part of the problem is for the Columbia group, the dipole sort of relative energy scale is around 1 nanokelvin, but their early experiments were more at the few hundred nanokelvin range. And so because of that, there are many, many partial waves, which would make this a very hard problem to treat quantum mechanically. In addition to that, you lose angular momentum conservation, and it becomes a very hard quantum three-body problem. But the two-body problem, at least, can find the adiabatic potential curve between two molecules and use that then in our three-body calculations. So this is what it looks like at the two-body level. This is not including a complete rotational basis. I think only up to about 6 states of angular momentum were included in this graph, which is why this doesn't keep going to infinity. But we're interested in coming in on the lowest of these plus. Every time two molecules collide, two polar molecules collide, should visualize they're going to be at these low temperatures almost entirely be this purple potential curve. And the experiment can prepare them in this plus state, so this is true. Now, one thing that happens for various detunings, especially the smaller Rabi frequencies, you get more and more two-bodied bound states. We sometimes call those tetramers, right? It's two polar molecules bound together. This is a kilohertz scale, so very, very weakly bound. And you can have three-body recombination into those states. And the couple of groups that have been studying this type of system, sodium rubidium or sodium cesium, they had a nice way to describe the two-body loss, like due to non-adiabaticity in this Hamiltonian. But there's a region at small ratio of detuning to Rabi frequency where their two-body model fails to capture everything. And there they could study it and see that this was actually three-body loss. So just to set the scale of things, as I mentioned, like for sodium cesium, the dipole typical energy is around a nanokelvin. There's a dipole length scale defined this way, 2 times the reduced mass times the effective dipole moment squared over h bar squared. This is going to be of the order of a few thousand Bohr, so it's very long range. And because these collisions are not deeply quantum, we have chosen to tackle this classically. using the toolkit that Jesus helped to develop when he was at Purdue. So to do two-body scattering in 3 dimensions, of course, we can separate center of mass and relative coordinates, and we have the concept of an impact parameter. For every collision, and then you can, sorry about this, you can develop the probability for a collision to happen at each impact parameter and incident momentum, multiply that by 2 pi times b dB and integrate, and you can get the total cross-section for various processes that are of interest. This has to, of course, get generalized to higher dimensional scattering, and Jesus's paper does that. We can think of it either as all these particles, or we can think of it as one body in higher number of dimensions. And that's more or less how we think about it in hyperspherical coordinates. And you have to generalize the formula for 3-dimensional scattering to this kind of structure, which is the same basic ideas, but just generalized to higher dimensions. So cross sections now don't have dimensions of area. They have these additional higher dimensions. Okay, so we have to calculate an opacity function by sampling over Monte Carlo trajectories, over initial momenta, over initial impact parameters, and so on. And we could use that in the end to calculate the recombination rate and thermally average it to try to compare with experiment. By the way, there is a clock in this room. Okay. One thing that we realized before we even wanted to start comparing with experimental data is that there is one fundamental flaw about the classical calculation, which is because you don't have quantized dimer energy levels that you can recombine into, you could have arbitrarily weakly bound molecules, I guess I should call them tetramers, that would be formed in the 3-dipole recombination process. And of course, if they're less weakly bound than the temperature of the gas, you expect them to be immediately dissociated and not to contribute to the molecule loss, dipole molecule loss from the trap. So we did find a prescription for the removal of these extra kind of low energy, very weak binding, which are kind of unphysical for 2 reasons. One is that there are no dimer bound states that weakly bound typically. And the other reason is that they would be destroyed immediately if they were there. Okay, so anyway, this purple group is the actual simulation after making this correction for the conditions of the experiment. Okay, so here are some of the results that we compare with the Columbia group experiments, which we were somewhat pleased. They seem to capture a lot of the right physics, this classical calculation, carried out mostly by Chamal. And so we wanted to study the systematic dependence, for instance, on the ratio of detuning to Rabi frequency. And well, you can see it's not really perfect, but the general trends are pretty well in agreement. And even the overall magnitude of the recombination rate obtained is coming out in pretty good agreement with the experiment for many different.
So blue is your calculation, and then the data points are experiments.
That's right. I'm trying to remember how we set the error bar on the, I think maybe the error bar on the blue in our calculation is because there was some uncertainty in, what was it in, I forget if it was the temperature or the detuning, I don't remember now.
Chris, what question? So you have these regions where you have a number of tetramer bound states. Is this where these, is that what it means? Is that you have
Oh, right.
between these dashed lines? you
That's
have-
right, yeah, that's right. As the tuning gets smaller, you get more bound states. So yeah, that's what these numbers mean. Thanks for reminding me to mention that. Some of the things that we wanted to check, and this is just comparing theory to theory, is that you can find kind of dimensional analysis scaling laws. Essentially, if you assume that any trajectory with impact parameter less than this B maximum will undergo a recombination event, then by equating the collision energy with the dipole scaling energy d squared over r cubed, that gives a B maximum that should scale like d squared over the kinetic energy of collision to the 1/3 power. And the generalized three-body recombination cross section should scale like this 5/3 power of d squared over the energy. And that leads to a three-body recombination rate that should, rate coefficient that should scale like the dipole to the 10/3 power and the energy to the -7/6. So this is checking that, and then of course the Boltzmann scaling will also mirror the energy scaling. So we found the temperature scaling worked pretty accurately when we don't subtract those extra very low binding energy events. And again, this is, the dots are from the Monte Carlo calculation, classical, and the dashed is the analytical prediction from the scaling law. The scaling with effective dipole moment was not as accurate. We aren't sure why, but this blue is, I think, the expected slope. The actual seems to follow a different slope slightly. We haven't really been able to figure out why there's this discrepancy.
Chris?
Yeah.
Is this dependence on temperature and dipole moment, is it fit or is it analytical? This T to the -7/6.
This is, I mean, we only fitted the overall coefficient. So, yeah. The dash is the analytical expectation, and the blue, sorry, in this case, the blue is the analytical prediction, I think. And the dash is the expected, sorry, is the reality fitting to that straight line to that. And here is now comparing with, I guess, what we might view as reality, comparing with the actual Columbia experiment. The temperature dependence comes out pretty nice. So we started this collaboration. We were talking for a year how hard this problem was. We were frustrated. We worked like crazy, and we had a hard time really finding a strategy to tackle this problem. One of the hardest we've treated in a few years. And just as we were starting to get results, they found they don't need us after all. That they just have to add a second microwave field and they can eliminate all of these bound states that were causing the recombination losses. So this led to, one of the strongest papers last year, I think, from the Columbia group, where they made the first BEC of polar molecules by adding the second microwave field. But they were nice and said, well, we'll publish our little recombination result with you guys anyway. So anyway, but no one cares now because you just add the second microwave field and you don't have to worry about it. But in the meantime, they have gone to colder temperatures. So now I'm showing you some unpublished work. that we're trying to take this to the quantum realm, because now they really have improved their experiment. They can come down into the few nanokelvin, or at least 10 nanokelvin, I think, in their current experiment. And so we've decided to tackle with this ambitious student, Shaimal Singh, the quantum recombination calculation. One thing that was helped a lot, there's this really nice paper by a Chinese group which finds an analytical potential between each pair of molecules. And so we are making use of this in our newest calculations, and can compare that to the exact potential, and this analytical approximation you can see works quite well. So we have some preliminary results with that. Here are the adiabatic potential curves in the lowest angular momentum symmetry, J equals 0, even parity. Again, J is not a good quantum number, but these are the states with the most content of L equals 0. And you can see that even though the two-body potentials don't have any bound states, you do get attraction in the three-body system. So it's kind of a Baromean type system, and this relates to the Efimov effect. Here is, if you multiply R squared and the mass twice the mass times the potential and add a fourth, you should get this -1 value if there is an Efimov effect. And you see that it looks like there will be Efimov effects for bound states in the sort of 10 to 100 dipole lengths. Okay, so that's scattering lengths that are in distance scales of the order of 40,000 Bohr. So it might be hard to see, but anyway, we think there should be an Efimov effect in the system, and we're trying to quantify that and see if we can find a more experimentally accessible range. This is all preliminary though, don't quote me on this. But I think it's pretty solid. Okay, I think I have a little time for topic number 2. Let's switch gears and think about the modification of threshold phenomena that occurs when you go to unitarity, the unitary limit. We've kind of had several papers in recent years that have used this language that Efimov physics goes beyond this infinite geometric series of bound states you get at unitarity. You can think much more generally that there is always in hyperspherical coordinates a 1/r² long-range potential curve in the dominant low energy channel in the ultra cold. And what happens when you go to unitarity is the coefficient of that 1/r² potential is reduced in many channels. In the case of the Efimov effect, it's reduced to actually become a negative coefficient of 1/r². In many other systems, including fermionic systems, it's reduced but not negative. So you don't get the infinite series of bound states, but you can see a modified Wigner type threshold law. And these papers all discuss that. So we like to write our long-range potential curve in this form in the dominant low energy channel as an effective orbital angular momentum. It's not really an angular momentum, so we just think of it as a centrifugal constant controlling the centrifugal barrier at long range. In all of these systems that have a scattering length, the next order correction looks like a constant times the scattering length, if there's only one scattering length in the system, divided by r³. In the systems with fermions, there's a scattering volume correction, 1/r⁵. But I'll focus here on the scattering length situation. Okay, so crank up A to infinity, obviously something has to change, and what changes is that L effective gets reduced. And for the bosons, it's reduced from 3/2 is the effective L for 3 non-interacting bosons. That gets changed to this minus S naught squared minus 1/4, where S naught is approximately 1. And that gives the infinite set of bound states. For other systems like 3 two-component fermions and 2 spin components like neutrons, which I'll be discussing, the L effective would be 5/2 in the lowest channel for a non-interacting or finite interacting. And that changes to 1.275 if you go to unitarity. For the 4 neutron system or 4 two-component, potassium atoms, like in the old Debbie-Ginn experiments, L effective changes from 5 by what we're calling this Efimovian reduction at unitarity to 2.027. Anyway, we have big tables in many of these papers, especially with Yu-Sin Chen, looking at all the different symmetries and seeing how the different grand angle momentum states, how their L effective changes at unitarity. Some are not changed, which basically have nodes at the interaction points. So one question is, under what conditions can you actually observe the unitarity modification of a threshold law? And we have a preprint, it just came out today on the archive, dealing with the pion capture by a triton, which converts the proton into a neutron in gamma ray and immediately produces instantaneously 3 neutrons. And you can look at the energy of those neutrons and see how that scales with energy, that production rate. Part of our interest was motivated by this paper by Hans Werner Hammer and Dam Sun, who have related this to an idea of Howard Georgi called the unparticle, which I'm not a real big fan of this term, but in any case, I don't think you should think of 3 continuum particles as a unparticle or non-particle, but that's kind of the language that they're using. Anyway, they tried to fit some very nice calculations by Golok, a Polish group and collaborators, and saw sort of agreement with the unitarity expected threshold law and no agreement with the E-cubed, which you would expect for a finite scattering length system. We felt we should study this farther because we had some evidence that you weren't so close to unitarity yet. So we had already studied the 3 neutron and 4 neutron in hyperspherical and found these magenta potential curves. And you can see that we also plot the non-interacting potential or finite long-range interacting potential and the unitarity limit. And while you are somewhat toward the unitary limit, you're really not there yet in either the 3 neutron or the 4 neutron system. So we wanted to look at this more carefully, like go to a log scale and really look at the low energy behavior. And this Golok group, they carried out a few extra lower energy calculations that weren't in their first paper. And we compared that with the expected threshold behavior from our hyperspherical potential curve, which is this blue curve. And you see it captures pretty well the turnover from the E-cubed law, which has to hold at very, very low energy over it. And it never quite really reaches the unitary limit, which would be this curve. So we think it was a little bit maybe premature for Hammer and Son to claim that the Golok paper had in fact observed the unitarity limiting threshold law, because really that threshold region is only below 1 MeV, and they really weren't comparing enough really right in that region and in enough detail like you can with a log-log plot. So I think I'm probably getting low on time, but one way we looked at this was to introduce this quantity, which basically an effective energy dependent exponent as the k times the k derivative of the log of the absolute value of psi in our hyperspherical energy dependent hyperspherical calculation in the adiabatic approximation. And you see that this is for real neutrons, this is what this curve looks like, and it never quite gets down to the unitarity limit over this sort of 1 to 2 MeV maximum range that you would expect the threshold law to apply to. If you go to 5, we also did calculations with like 5, 10, 50 times the actual neutron scattering length, which by the way is around minus 19 Fermis, compared to the effective range of about 2.8. Then you could start to get like probably 5 times scattering length of getting close to 100 femtometers. You might start to see it in this system, but no one knows how to make neutrons have that scattering length. But maybe that could be done in the ultra cold. I guess I maybe should, well, I could maybe describe this. We also studied, you know, at what point is it not just a simple scaling law, but does the actual nodal structure as the continuum wave function nodes start to overlap the initial state, you expect there to be more than just a scaling law. And the actual shape of the wave function starts modifying. So here we did 2 calculations with kind of fake tritons, either with an energy close to the triton energy, this darker color, or with much less binding. You start to see the curvature is being caused as you vary from a simple power law by this nodal structure changing within the transition matrix element. We also did the analysis for 4 neutrons. Here is the potential curves we had found in our 4 neutron study a few years ago. Again, non-interacting unitarity, and you're even here in this energy range, you're closer to non-interacting than you are to unitarity. And so also although Hammer and Son said you would see the unitarity law exponent, we don't think you really would over the expected energy range of validity. Okay, so I think I'm ready to conclude. Basically, 3 interacting dipoles or more are a hard problem. Thankfully, Newtonian physics does approximate the quantum world fairly well and can be done more easily in some cases. So we are posing the question whether an FMR state could be observable for 3 microwave shielded dipoles. We think they do exist. Whether they can be seen in the lab probably hinges on whether we can find something at smaller scattering lengths. There is an interesting paper on the archive by Xiaoling Hui, who's a bright Chinese physicist, theorist, saying that there could not be an FMR effect. So we already have controversy and excitement. We have to resolve this question. Interesting, the conformal field theory method of Hammer and Son, it does predict the same modified Wigner threshold law at unitarity, but we believe, in contrast to what they say in their paper, that a system of n neutrons is not close enough to unitarity to see that modification. But it would be interesting for the AMO groups to look for this modification because they can get much closer to unitarity. Thanks for listening.
Please, for a wonderful talk. Time for questions, please. Okay, Jose first.
Just a quick question about this ion capture, the 2-body potential pseudo potentials that are used in the hyperspherical.
For the neutron-neutron interaction? Yeah, there are known force fields, of course, for all the nucleons. We use the standard argon version 8, I think it's called 8 prime. We also actually checked, and it turns out you can get exactly the same potential curves if you just throw away that complicated thing and use a Gaussian tuned to the right scattering length. It's indistinguishable hyperspherical potential curves.
Greene, please.
Yes. You say that the classical trajectory method overestimates the three-body rate, and you make correction. So what is magnitude of the correction at low temperature?
Well, it was, you could see the fraction of events that were there. It's this one graph I showed. This one. So we threw out these events and changed this orange to this. That's at least, yeah, 400 nanokelvin.
And sorry, yeah, I will ask you more questions about it. I didn't understand exactly how you make the correction, so that.
Yeah, I believe it was mostly a temperature argument that compared the binding energy of the molecules produced to the temperature. And then there was some fraction, and I'm not sure I remember, but I think it stated in the paper how we chose that fraction.
One quick one follow-up to this plot there. I mean, if you try to do that semi-classically, wouldn't be able to recover these purple beans?
What do you mean by semi-classically?
Like to try to do like a WKB kind of arguments in order, you know, because you said the argument is like you have all these counts because if you treat it classically, you have this available infinite number of timer states near threshold. But if you try to,
I don't know, how do we change the classical calculation into a semi-classic? Because the classical calculation produces a bound state. Here, there is none.
okay.
Maybe you have a prescription, like group these into bins, say these would be this, in this case, this weakest bound state. These would be that one.
Yeah, no, anyway, yeah. Okay. Maybe it wasn't stupid.
Thank you. Please, could you comment please on this discrepancy that you described with the Chinese group? Is it just a numerical
Discrepancy. Oh,
with the Chinese group that predicted no existence of ephemeral physics in this model? Is it
I'm not
based
sure
on
I can
numerical?
comment very much. I didn't understand their arguments very well.
In the process you described with the three protons, so to say, and getting 3 neutrons, there's charge missing, right?
It wasn't 3 protons. It was just 1 proton in the triton, right? Converted by its interaction with the pi meson that converted that 1 proton into a neutron, but then all 3 neutrons were.
Okay, this is
just
why
to
charge
correct
is
you.
then conserved once again, because this is 1 proton.
Right.
There was a pi minus, so I was confused.
Right.
Thank you.
Oh, yeah, I didn't actually explain the process. We're proposing to see this 4 neutron case, but you could at least imagine a Gedanken experiment where you had an alpha particle bound to 2 pi minus mesons. And of course, most of the time they would probably be captured 1 at a time, but there would at least be some tiny fraction where both pi mesons would be captured at once. And then it would make a 4 neutron system at low energy. No experimentalists are beating down the door to do that experiment though.
If not, let's then please again